So in this lecture, we want to look at the modern atomic theory and some trends in the periodic table. Basically, the idea is to look at the structure of the atom and see exactly where electrons, protons, and neutrons are. So we have seen briefly before that the neutrons and protons are in the center of the atom in the nucleus, and we also mentioned that electrons basically spin around the nucleus. But in this lecture, we want to pay closer attention to the location of the electrons. We want to talk about energy levels and the number of electrons that can fit in each energy level. And we also want to look at properties of the elements, ions, and atoms based on the structure of the atom and where the electrons are, what the energy of the electrons are. So we're going to start with a brief description of electromagnetic radiation. The reason is because we want to explain the movement of the electron, so we need to know what a wave is like. We start with Bohr atom, which is the first atomic model that was given. We talk about the principles of the Bohr model, and then we move on to the modern atomic theory, which is a lot different from Bohr model of the atom, but some principles are still the same. So let's look at electromagnetic radiation. So electromagnetic radiation is a form of energy that runs a continuum from radio to X-ray, visible light to microwave. So the important parts of the electromagnetic radiation, since it's going to move like a wave, it's going to be the wavelength, frequency, and speed. Now, this is the wavic motion of a radiation. So the wavelength is marked on this slide here. So the wavelength is considered the distance between consecutive peaks of the wave. Now, let's focus on the electromagnetic spectrum. So the spectrum that you see here contains all the radiations that are known to us. So gamma rays are the ones that have the highest energy, and radio waves are those that have the lowest energy. Now, you also see the wavelength. The numbers on this spectrum here are the wavelengths for radiation. So for gamma rays, for example, the wavelength is 10 to the negative 12 until you get to radio wave, which is 10 to the 4th. Now, in this spectrum here, we have the visible region, so meaning that if the light has this particular wavelength that's within the visible region, we can see, and these are the different colors that we can see in the visible region. So what I want to bring your attention to is that the motion, properties, behavior of all this radiation is the same. They all move like a wave and they have the same properties, same motion. What is different in between these different radiation is the wavelength of this radiation, and wavelength actually affects the energy of this radiation. So the reason gamma rays are extremely, dangerous to us, whereas the radio waves are not, is just because of the energy of the gamma rays. Gamma rays have very high energy. They can penetrate, through our body, whereas radio waves, radio frequencies, they don't have a high energy, so they can't even pass through our skin. So the nature of all this radiation is the same. What is different among this is their energy, and the energy difference comes from the difference in the wavelength of these radiations. So you can find the energy of each one of these radiations. So energy is hc over lambda. H is a Planck's constant. C is the speed of light. And lambda is wavelength. So as you see here, energy and lambda wavelength are inversely related. The smaller the wavelength, the higher the energy. Now let's see why this is important. For now, we're going to focus on the visible region. I want to show you how the atomic theory, or the Moore model, was developed. So the observation was that, if you look through a light with a prism, you're going to see multiple lines, and each line has a different color. So the question for scientists were that, why do we see, first of all, multiple lines, and why do these lines have different colors in them? So we want to show you that basically the multiple lines represent the different energy levels in the atom, and the color of these lines basically come from the difference in the wavelength or energy of these lines. So this was the start of the development of the atomic theory. So Bohr was the scientist that came up with a model for the atom, and he suggested that basically nucleus is still in the center of the atom. Protons and neutrons are in the nucleus, but he suggested that around the nucleus, in the structure of the atom, there are different energy levels, and basically electrons sit on these energy levels and spin around the nucleus. So the energy level that's closest to the nucleus has the lowest energy, and as you get further away from the nucleus, the energy increases. So the energy of the energy level increases, therefore the energy of the electrons that reside in those energy levels increases too. Now let's see why Bohr thought or saw the necessity for different energy levels in the atom. So we're going to explain or define a couple of different phenomena here, relaxation and excitation. So Bohr suggested that energy can be absorbed or emitted by an atom, and the energy that's being absorbed or emitted is quantized energy, meaning that it has a fixed unit. So Bohr suggested basically that the electrons in the structure of the atom, they have the ability to transfer in between the energy levels. Now, the diagram you see here is a representation of the energy level. Just assume that here is the nucleus. Here is your nucleus. Instead of having those orbits, we're just focusing on a small part of that orbit. So we're just going to do the straight line. Now, the vertical axis, y-axis, is your energy axis. So these energy levels, grounded state, excited state, this represents the energy levels around the atom. Now, the energy level that's closest to the nucleus is going to be the grounded state. Grounded state has the lowest energy possible. And as you get further away from the nucleus, the energy increases. So now Bohr suggested that electrons can transfer in between energy levels. Let's just assume that you have an electron that's sitting in the first energy level. So the energy of this electron equals to the energy of the first energy level. Now, if we shoot a beam at this electron, the electron is going to absorb the energy of that beam. And as soon as the electron absorbs that energy, the energy of the electron is going to increase. Now, once the energy of the electron increases, that energy is not going to match the energy of the first level. So the electron is going to go up to an energy level where his energy matches. So let's say that electron from the first energy level is going to absorb energy and go all the way to the second energy level. Now at the second energy level, the energy of the electron now is higher. So the electron is going to stay in second energy level as long as I have the source to supply energy to the electron. Now, as soon as I cut that source or reduce the source of energy that's giving energy to the electron is not going to stay on that second energy level because it doesn't have enough energy, and it's going to go back or fall back to energy levels with lower energy. So if I cut off the energy completely, the source of energy, your electron is gonna drop back to the first energy level. Now this dropping back to the first energy level could be all in one step, or the electron can, drop to the first energy level first, and then from the first energy level to the ground state. Now, two things is happening here. First of all, we're providing or supplying energy to the electron. It goes to a higher energy level. That's called excitation. So you're basically exciting an electron to go from a lower energy level to a higher energy level. So excitation is through absorption of energy. To excite an electron needs to absorb energy to go to a higher energy level. Now, those higher energy levels are called excited states. Now, we also see that electrons on excited states are not all that stable. So they want to lose that energy and drop back to lower energy levels. So when you go from a higher energy level to a lower energy level, that's called relaxation. Through relaxation, energy is released. Now, this energy that's being absorbed or released, depending on how much energy is absorbed or released, if this falls within the visible region, we will be able to see lines. So the reason we see different colors is because from each one of these relaxations, different amount of energy is released. Different amount of energy meaning different wavelengths. So the colors are going to be different. And the reason we see multiple lines is because there are multiple transfer, excitation, relaxations that are possible in the structure of the atom. Now, the lowest energy level is called the ground state. And keep in mind that the ground state is the most stable state. So in our theory, in the atomic theory and in general in universe, lowest energy means the most stability. So the driving force is always going towards the lowest energy, which has the highest stability. Now, each line in the spectrum corresponds to emission of energy as an electron relaxes from a higher energy level to a lower energy level. Now, the color of the light depends on the energy that's being released. So Bohr's model, just what we show you, perfectly explained the the emissions, the lights, and the colors. But Bohr's model had lots of weaknesses too. So Bohr's model basically worked only for the hydrogen atom, which only had one electron, and it worked perfectly. But for, let's say, helium, as soon as you get 2 electrons, the Bohr model wasn't able to explain all the characteristics and behaviors of the helium atom or the rest of the elements in the periodic table. So that's when scientists started studying more to understand the properties and nature of the electrons and the atoms better. 2 things that helped the development of the modern atomic theory or quantum theory are 2 things: the dual particle nature of the matter. So basically saying that electrons are like particles. Particle is anything that has a mass, but at the same time they move like a wave. So what that ends up being is that we can't actually tell exactly where the electrons are at any moment. So that's Heisenberg's uncertainty theory, that it's impossible for us to know the location and the time of the electron at the same moment. There is always uncertainty because the electrons move like a wave all over the place. So what they leave behind is just a cloud of electrons. So we can't look at the electrons just as one particle and see where they actually reside, because they have the waving motion. They are the particles that have the waving motion, and they move very fast, the speed of light. So what we see is the cloud of electrons that are left behind. Now, quantum mechanics deals with the probability of finding the electrons, because we can't tell exactly where the electrons are. We're looking at the probability. What is the most probable place to find the electrons? Now, in this quantum theory, we also don't believe in discrete energy levels like Bohr suggested. Bohr suggested discrete energy levels, and he almost said that there are empty spaces in between those energy levels. But now, since we know that the electrons move like, waves, those are particles that move like wave, they occupy lots and lots of space. The space in which the probability of finding the electron is the most is called the orbital. So, since orbitals are going to be where the electrons are going to be, what's important is understanding or studying these orbitals perfectly. We want to know what the shape of these orbitals are. We want to know what their size is. We want to know what the energy of these orbitals are, because the energy and size of these orbitals define the energy of your electron and the number of electrons that you can basically fit inside these orbitals. So our goal in this lecture is going to be understanding orbitals, knowing how many orbitals we have, in each atom, what their energy is, what their shape is, and what their size is. Once we understand these orbitals and their properties perfectly, then we can start putting electrons inside these orbitals, and then we can look at the properties or structure of the atom. So let's focus one more time on the difference between Bohr models and quantum mechanics. As I mentioned, Bohr believed in discrete energy levels, whereas in quantum mechanics, the whole distance in between energy level 1 and 2 is called the orbital. So the electron can't be on just N1 or N2. Electron could be anywhere in between energy level 1 and 2. So in quantum mechanics, we still believe in energy levels. We still believe that the energy level closest to the nucleus has the lowest energy. And as you get further away from the nucleus, the energy increases. The only difference is that we don't believe in discrete energy levels. It's a continuous. So energy level 1 is going to be the entire space where the probability of finding the electron is the most. Also, there is no margin in between energy level 1 and 2. So there is no place that I can, point to and say, right here, energy level 1 finishes and energy level 2 starts. It's a gradual, shift from energy level 1 to energy level 2. So keep in mind that our principle is that electrons, they have a dual property. They are waves that move like, they are particles that move like wave. So what they leave behind is a cloud of electrons. So we want to look at the space in which the probability of finding the electron is the most. That space is called orbitals. Remember that we have different energy levels in the atom. Those energy levels are not discrete energy levels. So now, based on these fundamentals, let's look more into these energy levels, the energy levels that we're defining, orbitals, and look at the properties of the orbitals. Now, energy levels, we show them with N. And as I said, the energy level N equals to 1 is going to be the ground state. And this is the energy level closest to the nucleus. And it has the lowest energy. So N equals to 2, N equals to 3 and 4. So that's, as you get further away from the nucleus, the energy increases. Now, since our energy levels are just space now, they're not just one discrete orbit, they're space, the size of this space becomes important. So the space can be divided into sublevels. And each sublevel corresponds to a different type of orbitals that can basically house the electrons. So we want to know that in each energy level, what are the possible sublevels that we can have. So in energy level 1, we can only have one sublevel. That one sublevel is called S. So in energy level 1, there is only one sublevel. That sublevel is S. S sublevel composed of one orbital, and you can have a maximum of 2 electrons in that one orbital. So per each orbital, you can have a maximum of 2 electrons per each orbital. Now S sublevel has only one orbital, so the maximum number of electrons you can put in it is 2. So energy level 1, you only have the S sublevel, one sublevel. S sublevel composed of only one orbital, and you can put a maximum of 2 electrons inside that orbital. Now what you also see on this slide is the shape of the S orbital. So since it is in 3 dimensions, and also remember in our theory, atoms, molecules, ions, everything is spherical. So S orbital is spherical too. And since it's spherical, if you look at it through X, Y, or Z axis, it will still look spherical. So that's why you only have one S orbital. Now let's look at the number of electrons we can put in each orbital. So I already mentioned that the maximum number of electrons you can put in each orbital is 2. So we can show each orbital with a box, and we're going to use box representation for each orbital. And since S sublevel can only have one orbital, you expect one box for S, and the maximum number of electrons you can put in each box is 2 electrons. Now electrons, we show them with arrows. These are just representations. Now the electrons can have different spin. So what does that mean? In simple words, electrons spin around the nucleus, but keep in mind that while they spin around the nucleus, they spin around their own axis as well. Now when they spin around their own axis, they could spin like either clockwise or counterclockwise, and we don't really know if the electron is spinning clockwise or counterclockwise. But energy wise, if we have 2 electrons, we want these 2 electrons to have opposite spin. Opposite spin is the most stable state for the electrons in the same orbital. Now, how do I show the electrons have opposite spins? By the arrow, one pointing up, one pointing down. Now, it doesn't matter if pointing up is clockwise or counterclockwise. It's just being consistent. These are just representations, and you guys in this class don't learn how to find the spin of the electron. What's important is that if you have 2 electrons in one orbital, they have to have opposite spin. So they can't both be pointing up or both pointing down. This is called Pauli exclusion rule. So from here on, in any orbital, if you have 2 electrons in the orbital, which is the maximum number of electrons in each orbital, they have to have opposite spin. So that's called Pauli exclusion rule. Now we're going to learn more rules which will help us come up with the electronic configuration of each atom. Now, so this is for energy level 1. So for n equals to 1, which is the ground state, closest energy level to the nucleus, you only expect S sublevel. And in S sublevel, there is only one orbital, S orbital, that's spherical. And the maximum number of electrons you can fit in it is 2. Now, how do I show the maximum number of electrons I can fit in the S orbital? 2. And you read this as S2. Now, if it is the S orbital in the first energy level, I say 1s2. So 1 represents the energy level. S is your orbital for the sublevel, and 2 is the number of electrons. We will practice more on this. So in energy level 1, we only have one sublevel, that's S sublevel, and S sublevel has only one orbital. Therefore, the maximum number of electrons we can fit in the first energy levels are 2, because we only have one orbital in the first energy level. Now, let's move on to the second energy level. In the second energy level, since you're getting further away from the nucleus, second energy level is bigger than the first energy level. Bigger meaning that there is a possibility for more than one sublevel, and also it means that you can put more electrons in the second energy level as well. Now there are 2 sublevels or orbitals in the second energy level, 2s and 2p. Why 2s and 2p? This 2 is because we're at energy level 2. So in the second energy level, you expect two sublevels S and P. We call those 2s and 2p because they are in the second energy level. So the 2 represents the energy level. Now for the 2s, we already know that the maximum number of electrons in the 2s is going to be 2 electrons. The 2s orbital in the second energy level is the same as the one in the first energy level. It's just their energies are different. But it's still spherical. The maximum number of electrons you can fit in it are going to be 2 electrons. The other sublevel is the p sublevel in the second energy level. Now, the p sublevel looks like dumbbells. So, since it looks like dumbbells, as you see on the slide, it has, it looks different if you look through it from an x, y, and z axis. So for the s sublevel, we would expect 3 different p orbitals, px, py, and pz. So what does that mean? It means that, let's say if this is your x, y, and z, if your p orbital is along the x-axis, this becomes a px. If your p orbital is along the y-axis, it becomes a py. If the p orbital is along the z-axis, it becomes the pz. Now, if I put all 3 of them together, you're gonna end up with the p orbital. So p sublevel has 3 orbitals in it. So if I want to show this with boxes, I would show a box, 3 of them, and each one of these represents px, py, and pz. So each p sublevel has 3 orbitals in it, px, py, and pz. Now remember that in each orbital, you can put a maximum of 2 electrons. So 2 here, 2 here, and 2 here. So you can have a maximum of 6 electrons for a p sublevel. So for energy level 2 n equals to 2, we have 2s and 2p. Maximum of 2 electrons for s, maximum of 6 electrons for p. You read this as 2s2, 2p6. Now, in the third energy level, since it's even bigger, you would expect 3 sublevels, S, P, and D. So each D sublevel composed of 5 orbitals, dxy, dxz, dyz, dz square, and dx square minus y square. So since you have 5 different orbitals for D sublevel, and you can fit a maximum of 2 electrons inside each orbital, you would expect a maximum of 10 electrons for a D sublevel. So we're gonna use these sublevels and orbitals we learned in order to write the electronic configuration of different elements or ions. So the way we're going to write this, or the way the electrons are going to fill out these orbitals, is based on the energy. The orbitals that have the lowest energy are going to fill up first, and then if you have enough electrons, the orbitals with the higher energy are going to fill up next. So this is the order in which the orbitals are going to fill up in general. So first, the lowest energy level is the first energy level. In the first energy level, we only had the S sublevel. Maximum electron you could put in it was 2. Now, I don't expect any more sublevel in the first energy level, so we're going to move to the second energy level. In the second energy level, we expected 2s and 2p. Those are the only sublevels we expected in the second energy level. In the s orbital, we can have a maximum of 2 electrons. In the p sublevel, we expected a maximum of 6 electrons. Now, after second energy level, we're going to move to the third energy level. In the third energy level, we expected 3s, 3p, and 3d. In the s, you would expect 2 electrons maximum of 6 in the p, and maximum of 10 in the d. Now, moving on to the fourth energy level, we expect 4 sublevels here, 4s, 4p, 4d, and 4f. S, you would expect a maximum of 2, maximum of 6 electrons for p, maximum of 10 for the d, and maximum of 14 for the f. Now, in general, this is the order in which the orbitals line up in terms of energy. But we want to show you that there are some exceptions here. And as we teach, we show you what the exceptions are. So one exception is going to be here. These two are going to switch. So the order, the actual order that you want to memorize is like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4s2, 4p6, and it's good for now. So memorize this, the order, and this is called the electronic configuration. So we're going to write the electronic configuration for different elements, and then I'm going to show you, after we learn how to write it, I'm going to show you what information we can get from the electronic configuration. So one other thing that I want to mention here, again, in terms of the energy, because energy is important. So everything in the first energy level has lower energy than the second one. So n equals to 1 has lower energy than n equals to 2, n equals to 3, and n equals to 4, so on and so forth. So here energy increases. So this has the lowest energy. Let's do it this way. This is lowest energy. This is highest energy. Now, in terms of the sublevels, S has lower energy than P, D, and F. Again, this is lowest energy, and this has the highest energy, or the energy increases. It's important to know the energies and ranking these orbitals based on their energies. So let's look at an example. What is the maximum number of electrons in a 4D sublevel? So whenever it's a D sublevel, remember that D sublevel composed of 5 orbitals. 1, 2, 3, 4, 5. And in each orbital, we can have a maximum of 2. So for any d sublevel, you can have a maximum of 10 electrons. What is the maximum number of electrons that can occupy the n equals to 3 sublevel? So in energy level 3, what is the maximum number of electrons we can have? So in energy level 3, remember that we have 3s, 3p, and 3d sublevels. Now we can have a maximum of 2 for s orbital, 6 for the p sublevel, and 10 for the d sublevel. So the maximum number of electrons that we can fit is 18.